Okay, so first of all, so these are very interesting, again, very restricted number of overlay structure that we can describe by wood notation. So there are a couple of cases. Case A is just that when the theta, the two mesh rotation angle is 0, there's no need for rotating to coincide the two things. We can then call this n by n. Or Pn by n, so-called primitive cell or primitive cell n by n. Or sometimes you can call it center n by n, depending on the mesh. So here we have a center mesh. If this red grid happen to completely overlay on top of the roof, right, completely on top of the roof, then what happens? Then you would have a primitive n by n. You have a primitive n by n. In other words, you would not be able to see, right? You will not be able to see very easily that whether you have a substrate or a absorbing structure that you have. Okay, because the red grid will now be directly on top of the green of the blue grid that you got. So when it's directly on top, you have primitive mesh, so-called primitive n by n, or just sometimes people just get lazy and drop the p, and then you have n by n. If you have, like a situation, you have move it right in the center of your blue grid, then you have c n by n, so-called center n by n. Okay, and if you don't have this theta angle not the same, not overlapping each other, then all you have to do is just n by n rotated by theta degree. So if you have a situation like this, you have, let's say this thing rotated by 45 degrees, then the whole mesh will rotate by 45 degrees. Then you would call it n by n r theta r45. Okay. So the point is that the wood notation only works for a very limited number of overlay structure, and it's not really general enough to describe everything that we see in nature. So we're going to have to use better notation. So I will tell you a little bit about that. But before that, there's an example that I want to show you. The example. So you have nickel 100, 1 by 1. So you always call nickel is a cubic structure. So you would have this 1 by 1. You can always call the substrate 1 by 1. Now if you put, so that's a clean surface, and if you put oxygen on top, and oxygen go on the P2 by 2 site, okay, set a primitive 2 by 2. So it has the same arrangement, if you like. Arrangement is a square arrangement. The oxygen atom go onto this nickel atom. In fact, form this. You can imagine it form this a top site, but we can go directly on top of the nickel atom, or directly in between two nickel atoms, so called the bridge site that you form here. And we'll talk a little bit about that. But then you also have silicon 100. If you have a clean surface, so in the nickel case, the nickel 100 is not reconstructed. So it's the ideal. So there's no XY movement on the cell edge, right? Whereas the clean 100 surface for silicon is reconstructed. So in the substrate, you would call silicon 100 1 by 1. But on the surface, you cannot call it 1 by 1 because the surface, the cell edge of the silicon 100 surface actually reconstructed and give you a 2 by 1, so-called 2 by 1 reconstruction. Okay. So that means that there are the unit cell, one of the vector is twice as long as the cell edge, on the top skin of the cell edge structure is twice as long compared to the top skin of your substrate structure of the silicon or within the silicon. Okay, so you have a reconstruction of the clean surface silicon 100. That's why people always designate silicon 100 2x1, so-called 2x1 structure. That's what they're talking about. They're talking about a reconstructed surface. If you're talking about nickel 100, they call it 1x1 structure, which means it's not a reconstructed surface. Now, interestingly, if you then put hydrogen atom on top of this silicon 100 2x1 clean surface, you actually get rid of this reconstruction. You revert the surface back into the same type of periodicity that you see on the top skin of the substrate layer. So you can have both. In other words, if you start off with a clean surface, you can get reconstruction by putting adsorbate on top, or you start off with reconstructed surface, you put atom on top, it actually de-reconstruct the original reconstruction. So nature occurs in either way. So you have to really know your system when you talk about that. And of course, silicon 100, this 2x1 structure is fundamental because this is how all the CPU are built based on silicon 100 wafer. All the semiconductor industry seriously use this type of service structure to construct their transistor and so forth on the silicon. So this is a fundamental surface that in the world, I mean, you control all the electronics that we use in so this wood notation is good. People use it a lot still. When you talk to service chemists, they use it. But it's not very general because if you have something tricky, it doesn't describe every surface, every overlay structure. So people come up with a different notation called the matrix notation, which is due to Park and May, and again in near the same time when Wood come up with this notation. This is a more general notation involving just a vector algebra, really. So you treat your overlay basis set, right? We use this jargon E1, E2 as a vector basis, and your substrate basis A1, A2, and you can imagine that I can have some sort of transformation starting with this A1, A2. I can build my B1, B2 by this sort of transformation. So I use a matrix. In matrix notation, it looks something like this. You just take this matrix, multiply by this vector. This is a column vector, and transform it to another vector. So that's how we use it. So you can give, so in the matrix notation, you just give this transformation matrix from your substrate vector, basis vector, into your overlay basis vector. And you can classify based on this matrix, particularly based on the determinant of this matrix. So the determinant of a 2x2 matrix is very simple. It's just the difference of the cross product. So this is a cross on this diagonal and this diagonal. So the matrix determinant is just the difference, right? This is a diagonal product minus the other diagonal product. That would be the determinant of the 2x2 matrix. And you can this determinant turn out to be an interesting number. This determinant, transformation determinant, turn out to be the area ratio between your overlay grid versus your substrate grid. Okay, so B and A here are the area of your unit cell for the overlay. That's B, right? And then A is the area of the unit cell for your substrate. Okay, so this determinant actually is quite useful because you can get a sense of how big your overlay unit cell with reference to the substrate unit cell will give you the ratio of the size, right, relative size, if you like, of the unit cell. So you can use this to provide a convenient public.